Hello, everyone. So I'm happy to see you during our second lecture. So in this lecture, we will hopefully get to uh, some properties of Gregorchy group. So we definitely will prove that it's infinite, and we'll probably will start proving that it's periodic group as well. So we will have to introduce a few more tools. So specifically, we will need to talk about sections of automorphisms and endomorphisms and about Ritz recursion. We'll talk about word problem, how to solve that in groups. We'll touch a little bit upon order problem. So I'll introduce AutomGRP package so that you don't have to do all the calculations by hands. You can actually use the computer here, and that's a gap package that is very useful. Right, and then I guess at the end of the meeting, we're gonna start talking about Grigorchi group in more details. All right, so before I start, let me just say one word. So I was talking to Neelam yesterday, and so she said that she made a small mistake in the recitation, and she asked me to just make a note on that. So when she was describing, when she was talking about the problem uh, on whether the group of all automorphisms generated by finite automata is actually a group. So you have to use the construction of a product of automata to show that the product of two automorphisms induced by finite automata is again induced by finite automaton. So there, so when she considered the product of two automata, initially I think she mentioned that that has to act on the product of alphabets. So that's not quite the case. So the product of those two automata actually acts on the same tree, right? So you don't change the alphabet, you just change the state set. Right, so that's for you to know. And again, if you have questions, the homework is due tonight, so I'll try to answer those questions. Just email either to me directly or to organizers, and they forward that to me. All right, so before we begin, are there any questions about the homework, about anything else? All right, so then let's start. Um, at the end of the last talk, I just finished with an example, non-trivial example of a group generated by an automaton or self-similar group. This is the Gregorchy group. So far, I'll just quickly review and remind that so this is our automaton, and so every state defines an automorphism of the tree X star, right? And now we generate the group by all of these automorphisms. So specifically, this is a five-state automaton. So this state here, ID, that's going to be corresponding to the trivial automorphism because it doesn't change any input letter. So 0 goes to 0, 1 goes to 1. And whatever you read, you go back to itself. So that's why, in terms of the generating set, there is no point to include this one in the generating set because it's just a trivial transformation. But these four, A, B, C, and D, those are the actual generators of Gregorchy group. Moreover, as we will see quite soon, if you take a product of any two of B, C, and D, you're going to get the third one. So B, C, and D actually generate a Klein 4 group. So actually, this group is 3 generated because, for example, D is equal to BC. And the full group is generated by A, B, and C. Right, but for symmetric purposes, usually people consider all A, B, C, and D. And so we're going to work with that generated set mostly. All right, so now we have definitions. Now the next question is, well, how to work with these groups, right? So uh, let me start with that. Okay, so maybe, you know what, I will try to use a different pen today. So I looked at the file and maybe it was a little bit hard to read. So I'm going to just be using a regular pen. Maybe it's not going to be as fancy, but maybe it's a little bit easier to read. Okay, so how to work with self-similar groups. So what I mean how to work, of course, I want to understand if I have an element, so whether that's a trivial element or not, how to multiply element, how to multiply elements, how to understand what is the automorphism or endomorphism generated by this element, and so on. So we need to define first a notion of a section. So, and that's something that is also a part of the homework, which is due tonight. So I think one of the problems asks to construct an automaton that induces a given endomorphism, right? And so there we have to use the notion of a section. So let's just go over that. Uh, so remember, before we started from an automaton, and then we showed that every initial automaton will act by automorphisms or endomorphisms on a tree. So here we're going to go in the opposite direction, right? So we will start from endomorphism of a tree, and then we will construct an automaton that defines that endomorphism, right? So we're going to have to use the notion of a section. So what is that? So well, let's say that first define a notion, the notion of a section of an endomorphism of X star. Okay, so well, suppose you have G, which is endomorphism, graph endomorphism of X star, right? Or of course you could have that G is in automorphisms of X star, right? And suppose that you have some vertex. Let's just start with X. X is in X. So we're just gonna state what happens for a letter. Okay, so what happens then? So well, G acts on the tree, right? So let's draw G. So this is our G. It somehow permutes vertices of the first level. And so there might be more than two, of course. So let's say that, so this is our first level. And maybe you have vertex X here. And then this vertex X got sent to another vertex G of X, right? G is an automorphism or endomorphism. So just 1 second. Let's just use the green for the action. Okay. So let's say that G sends X to G of X. Okay. So then there is a subtree hanging down from X, which is canonically isomorphic to the big tree. And then there is a tree, again, canonically isomorphic to the big tree hanging down from G of X, right? And suppose that you have some element, let's just do it not with a straight line, but just with some path. So this is xv, and xv got sent to, let's say, G of X v prime, right? So this vertex got sent over here. So if we identify this small tree with a big one and this small tree again with a big one, then we could just kind of disregard what happens with the first letter, and we could focus our attention on what happens with this path. So this path here corresponds to word V, and this path here corresponds to word V prime, right? So let's just say, for example, that in red. So this is V, and this is V prime, right? And the section of G at X will just send V to V prime. So basically, again, the whole subtree here is shifted to this subtree. But once we identify both of these subtrees with the big tree, we're going to get an endomorphism of the big tree again. And that endomorphism is called the section. So let's formally write it. So, so let's say for each V in X star, right? So this red V. Okay, and well, so we fixed already X, right? So there is V prime in X star such that G of XV is equal to g of x v prime, right? So then the map g sub x, so that's the notation for this section. Again, that's going to be the map from x star to x star, that you can check that this is an endomorphism of the tree again, that sends v to v prime is called the section of g at x. Okay. So that's the section at the vertices of the first level, but then of course you define more generally. Define for, let's say, v is equal to, maybe not, let's say not v, but w is equal to x1 and so on, xn. We define g sub w to be just g sub x1, and then you take another section at x2, another section x3, and so on, xn. Okay, so proposition, just move it up a little bit. Yeah, by the way, I will open the chat here so that I can see if you have questions. Chat. Okay. So for any g in endomorphisms of x star, or g in automorphisms in x star, so there are two propositions in one, and for any w in x star, we have that g sub w will be in endomorphisms of x star, or g sub w will be in automorphisms of x star. Okay, so for any automorphism or endomorphism and any vertex, a section is again an endomorphism or automorphism. So how to visualize it? Again, so you have a tree, you have W here, right? And then you just look at what happens under W. Yeah, this W will be moved to some other vertex here, right? And then whatever path was, let's just do red here, for example. So maybe I'm not too consistent with colors, but it's okay for this purpose. So this red will go to this red, right? So you just care what happens under W. Yeah, the whole tree sub here will be shifted to this one here. This one will be G of W, of course. G of W, right? But you care what happens with this path. Okay, so and then your homework problem was that if you construct an automaton from an endomorphism, then you're going to get an automaton that induces specifically this endomorphism, right? So let me just maybe mention that here. So one of the homework problems, but it's kind of conceptual problem, is that given G in, let's say, endomorphisms of X star, right, we define automaton AG, or maybe let me write it from a different line, AG, whose set of states is the set of sections, G sub V, for V is in X star, right? So you take all sections of your endomorphism where vertices run over all possible words, finite words over X. The alphabet is X, and now you have delta and lambda. Well, delta will be the following, so that's the transition function. So basically, you're going to transition from G sub V via X to G sub Vx, right? And if you read letter X, you're going to output letter, so G sub V of X. So because G sub V is an endomorphism of the tree, it acts on letters of the alphabet as well, because those are just words of length 1. And so G sub V of X, that's the action of G sub V on letter X. Okay. Right. And so basically this is lambda here as well. So this transition encompasses both delta and lambda. And the initial state is G, that's initial state. Right. Okay. So that's part of the homework problem, right? And so it could happen that this automaton could be finite or it could be infinite, because the set of states here, the set of sections, could be finite or infinite. So, and so some authors actually have a name. So sometimes people call these groups not self-similar, but state-closed groups, so that the set of states actually is closed. The group is closed under taken sections. Right. Right. So well, let's see. So now we define sections, and now let's maybe talk about with recursion. So once we define sections, we want to describe, so goal is to formalize the following expression. So if you have an automorphism or endomorphism G, right, then it has sections here, let's say G sub 0, G sub 1, and so on G. Maybe, you know what, so let's just say that alphabet is 1 to D, so that it's a little bit easier. So G sub 1, G sub 2, G sub D, right? And then there is some permutation sigma here that permutes these subtrees, right? So G sub 1 acts on this subtree, G sub 2 acts on this subtree, G sub D acts on this subtree, right? So you want to write G as G sub 1, G sub 2, and so on G sub D, and then sigma. Okay. That will describe the action of this endomorphism or automorphism on the rooted tree, right? It will just tell that on the left subtree you act as G sub 1, which is again an endomorphism of the tree. On the second subtree you act as G2, and so on. And after you act on these subtrees, you permute the subtrees according to the permutation sigma. So this will be called with recursion, right? But let's just formally define what it is. What is a with recursion? It comes from the standard classical notion in group theory called the with product. So again, I will not define the most general form. There are several variants of with products. I will specifically be talking about permutational with product. So to formalize it, so we define permutational with products. So what is that? So suppose you have two groups, G that acts on some set X and H that acts on some set Y. Okay. So definition. The group G with H, that's a notation for the with product. So now formally, for those of you who have taken some group theory in a little bit more advanced form and know what are semidirect products, I'll just write that this is G raised to the Y semidirect with H. But again, so there's no need to get into the details right now of the semidirect product. But so I will just describe what the action is. So this is a group, right? So whose elements are of this form. And this group acts, let's say acting on X cross Y. So in which H acts on G to the Y, right? So these are just multiple copies of G indexed by elements of Y, right? And remember that H acts on Y. So you have every element of H defines a permutation of Y. So what H does, it just takes this tuple of elements of G and permutes them according to the action of H on Y. So that's what we say here, in which H acts on G of Y by permuting the indices by permuting the indices in the tuples according to the action on Y. To the action on Y. Okay. Uh, so how to visualize it? Let's maybe draw the picture here. Okay, let's maybe I think it's fine. So how to visualize it? So you could think of one big circle corresponding to elements of Y. So those are elements of Y. And that's why it's called wreath product. You're going to see the picture now. So this is Y, right? And H will act on this big circle. But for every element of Y, there is a little circle corresponding to X. Okay, so that's going to be the action of element of G wreath H on this wreath, right? So every circle, that's just a copy of X. So elements of G wreath H are of the form. So you have a bunch of elements, let's say G1, G2, and so on, up to G, let's say, size of Y. Of course, Y could be infinite, but in our cases, Y will be finite. So that's why I will just write G sub Y. So you have a tuple, G sub 1, and so on, G size of Y. And then you have H, which is an element of H. So this guy is in G to the Y, and this guy is in H. Okay. And you multiply two such tuples, and you act on this tuple in the following way. You act by this couple on X cross Y in the following way. So first, you act on these little wheels. So, and the wheels correspond to X. So those are copies of X, right? You act on the first wheel by G1, by the first component of the pair. On the second wheel, you act by G2, and so on and so on. On the last wheel, you act by G sub Y, right? That's the first thing that you do. And then what you do, you permute the wheels according to permutation H, right? So here you have G1 kind of rotates this wheel, G2 rotates this wheel, and GH rotates this wheel. And then H will rotate the big wheel after that. Okay. So in general, this construction it plays an important role in a couple of subjects. So I think that at least uh, I think that the first one who actually used this construction was Lev Kaluzhin, who was a Ukrainian mathematician. So at some point, there is a urban legend that he invented that while being in concentration camp during World War II, while working on some sewing machine. Again, I don't have a confirmation of this, but that's what people used to say, at least. So he was interested specifically in understanding what are CeLO P subgroups of symmetric group of SP to the n for prime P. And so it turns out that CLP subgroup will be exactly the Ritz product, iterated Ritz product of cyclic groups of order P. And that's what we will have here as well. So it also plays an important role in the theory of semigroups as well, in Kroner-Roth's theory. Right. So why that's important? Because now understanding this action will tell us how to multiply two different elements. So you have one tuple element of elements of G, and then an element of H, and then you multiply by another element of this form. So and that will give us the multiplication formulas. Right. So and maybe let me just copy from here to the next page. Okay. This picture here. And I move to the next page. Okay. So this gives multiplication formulas. So in what way? So suppose you have, let's say, two elements of this permutational Ritz product. So suppose you have, let's say, G, which is equal to G1, G sub Y, and some element H, right? And another one, let's say G prime, which is equal to G1 prime, G sub Y prime, and let's say H prime, right? So then you want to see what will be the action of GG prime on this set X cross Y. So this wheel is essentially X cross Y, right? For every element of Y, there is a copy of X. So let's see how that works. So G prime then will act in the following way. So first you act by G, and the convention here is that we have right action. So Gx first and then G prime. It's a little bit not compatible with the standard composition of functions, but on the other hand, that's compatible with multiplication of permutations that is kind of standard. And in GAP, for example, multiplication of permutation is exactly done from left to right. So we're going to stick to that convention, but that's not uniform convention throughout the literature. Okay, so you act first by G and then by G prime. So let's see what happens. You take an element of a small wheel, right? You act first by G1, right? G1 will move it somewhere. And then you move the whole wheel to a different wheel by H. When you act on that by G prime, right? You act, so maybe I can just draw the action. Okay, so for example, you take G1, G1 is moved somewhere here, right? This point is moved by G1 to somewhere here, and then this point is moved somewhere here by H, right? So when you apply G prime, you act on this point already not by G1 prime, but by corresponding element of G primes that corresponds to this wheel, which is the image of H of this wheel, right? So formally, you could write it as G sub 1. So that should not be green, that should be black. So G1, and then instead of multiplying by G1 prime, you multiply by GH of 1 prime. And you do the same thing for the rest. So you have G2, GH of 2 prime, and so on, G sub Y times GH of sub Y prime. And then, of course, the action on the big wheel will be just a product of H and H prime. And that's just classical definition of the semi-direct product. Okay, so we probably will do one convention. So convention.
The
yeah.
action of coordinate is right?
I'm sorry, once again?
Is it right action? Yes.
Yeah, that's going to be right action. Yeah, so exactly. So first we act by G and then by G prime. Yeah, so convention, yeah, by the way, so before doing the convention, let me just say that you could also do the same formula for G inverse, right? So G inverse, if you want to construct an element of this permutational Ritz product that undoes what G did, so it's quite easy to see that that's going to be just G, oops, not G, but uh, it's going to be G H inverse of 1 inverse, and so on, G H inverse of Y inverse, and then you do H inverse. So if you multiply G by G inverse according to this rule, you're going to get the identity element. Right? So those are two important formulas for us that will basically tell us how to work with groups generated by automata or self-similar groups or semigroups. And so here, of course, I meant that this is a group, but the same thing works if you replace G and H by semigroups, and you can define the Ritz products of two semigroups exactly in the same way. Okay, so now convention. So there is too many brackets.
Excuse me, can I ask
Yeah.
what changes in inverse element in case of left action?
So if you consider the left action, then you have to swap the order of all of the products, right? So you're going to have not G, G prime, you're going to have G prime, G, and then everything else just follows exactly the same. You just, for every word that you see, you just swap you take the reverse of the word. So it's going to be isomorphic action, of course, and so the isomorphism will be done by swapping the order of letters in every word. So we just have to stick to some of the notation, some of the convention, and so here we consider right action, but again, as I said, some of the authors consider left actions as well. And sometimes when you have to talk about dual automata, you actually have to consider both actions because there's a construction called dual automata, which gives rise to the classes of reversible by reversible automata. And that's where, so here we have states and we have letters, and states act on letters. But you could reverse this and you could think of that as letters acting on states, right? And then it's more natural, for example, if you can consider left action for letters acting on states, then it's more natural to consider right action when you act on letters on states. Right, but again, so we probably will not have time for those details. So just to be a little bit simpler, I will just say that no, maybe conventions will come just a little bit later after we do some examples. Okay, of permutation of Ritz products. So well, let's just do, for example, oops, 1 second. Let's do, for example, SD, Ritz SD, where both SD act on just 1 to D. Right. So then you could consider this wheel, essentially. You have one wheel, which is our 1 to D, right? And then for each of these wheels, there is another wheel like that, right? So you could, maybe let me just use a wheel just to kind of bring the connection what we had to what we had. There is one wheel over here, and there is one wheel over here, and there is one wheel over here for each element of 1 to D, right? And we could visualize that as a rooted tree of degree of depth 2, right? And now we see what we have seen before. So we're talking just about automorphisms of this finite tree of depth 2, right? You have one element of SD, let's say sigma is in SD, symmetric group acting on 1 to D. And then for every element of 1 to D, there is, let's say, sigma 1, and so on, up to sigma D, right? So, and then the permutational Ritz product will have elements of the form sigma 1, and so on, sigma d, and then you have sigma again. So those will be elements of SD with SD. So we can randomly permute elements of each of these copies, right? And then after we permute elements of these copies of 1 to d, we can shuffle these copies accordingly. So that means that this group will be just the group of all automorphisms of this finite tree. So SD with SD is just automorphism group of a tree of depth 2. Okay, and now you could iterate this construction, so you could add more copies of SD, and you could do actually infinite number of copies of SD. So that's why the next example will be the full automorphism group. So example, automorphism group of X star. Again, you could do the same thing for endomorphism, but I will concentrate on automorphisms. So how does it work? So we know how the tree looks like, right? And we know that, so here we permute these subtrees by some element sigma in SD, right? And for each of these elements from 1 to d, we have another automorphism G sub 1, G sub 2, G sub d, right? So we act on these automorphisms, which are again automorphisms of X star on the subtrees, and then we shuffle the subtrees. So what we have is that this is naturally isomorphic to the wreath product of itself, out X star, with SD. Okay, where this decomposition basically tells how G acts on the subtrees and then how the subtrees are shuffled. Okay, so this map, this isomorphism, let's call it, I don't know, let's call it psi, for example, from aught X star to, and that's an isomorphism, to aught X star with SD. It sends G to this pair, G sub 1, G sub D. So here I will write sigma G, where sigma G is a permutation on X induced by G. This is permutation on X induced by G. And those are sections of G at X in X, at all vertices of the first level. And so the convention, because there are too many brackets, so convention is we're going to just write G as equal to G sub 1, and so on G sub D, and then sigma G, right? That's kind of the classical notation, which is called the wreath recursion. So this is wreath recursion for G. All right, so now these formulas here on top, how we multiply elements and how we take the inverse, of course, are applied in this specific situation, right? So we could still multiply two automorphism. We can take the inverse exactly in the same way. So let's maybe move to the next page. Maybe let me just take a copy of that so that
Does this mapping corresponds to splitting of various product on a first level? Splitting on semi-direct product.
Well, it's not a direct product, it's semi-direct product.
Splitting on semi-direct, I say semi-direct very quickly. Does it correspond to splitting on the first level?
Yeah. So that's exactly the point. So that so these elements they come from the automorphism of X star to the D, right? And this element comes from SD. So this wreath product is a semi-direct product of odd x star to the d, so that's the d tuple from there, and an element from the symmetric group, and we multiply this element according to these rules that we have described. And I was about to write down this rule specifically for this specific case. Yeah, but that's exactly just uh, that's exactly an instance of a wreath product, right? And we just use the notation essentially and the definition of the wreath product to work with groups generated by automata. Yeah, I'm not sure that I answered this question, but yes, so that's exactly the wreath product. Okay, so let me just move maybe this to the next page so that we have it. Copying. Let's insert it somewhere here. So this is our map. Right, now given G, which is equal to, let's say, G. And so, of course, G sub 1 with this bar, right, it denotes that we start with an endomorphism or automorphism G, and then we take a section, right? But in general, you could build new automorphism from other automorphisms, right? You could start with any G1 up to GD. You take any automorphisms, and then any permutation sigma G, right? Then that is a way to define this G, right? So there's really no need to put these bars over here. Yes, G1 will be G sub 1, but you could start with choosing arbitrary G1 up to GD, and that will give you the definition of G. Okay, and say if you have H, which is equal to, let's say, H1 up to HD sigma H, right? So then those formulas on the previous page, the product formulas, will give us that GH will be, so first you act by G1 on the left subtree, then the left subtree is moved somewhere, and then you act on the corresponding section of H on that subtree, right? So the first subtree is moved by sigma G to G sub 1 subtree, and then you act by H on that subtree. And so on, you have GD, H, sorry, not G of 1, let's say sigma G of 1. That's the same thing, of course, but just it's going to be a little bit easier to understand that we are specifically talking about this permutation. Sigma G of D, and here you just take a product sigma G, sigma H, okay? And G inverse will be equal to G sigma G inverse of 1 inverse, G sigma G inverse of D inverse, sigma G inverse. Okay. So these are probably the most important formulas for calculations in groups generated by automata, right? Well, maybe let's just do some examples and let's do some translations. So examples. Let's, for example, do adding machine. So you have tau, and then the state is ID, right? 0, 0, 1, 1. And then tau, if you read 0, you output 1 and you stay, you wait for 1, right? And if you read 1, you output 0, and then you stop thinking about the carryover, you go to the identity state, right? So you could also build a portrait of that. So a portrait of an endomorphism is just is a tree in which the vertices are labeled by the corresponding permutations induced by these sections. Okay, so this is tau, right? Tau permutes 0 to 1, 1 to 0, right? So that's why we'll just put a little switch here to emphasize that tau will permute the vertices of the first level. Now, if you read 0, yeah, sorry, so it's going to be, of course, the opposite. So every time I do this mistake, so if you read 1, you output 0 and you wait. And if you read 0, you output 1 and then you are done because you've added your 1. Right? So if you read 0, you go to 1. you output 1, so that's why you have this permutation, non-trivial permutation here, indicating that we flip these two vertices. And then you go to the identity state, right? So that's why here we're going to have identity state. Now, once we are in identity, there will be no more permutations, and identity goes to identity, identity goes to identity, and so on. So this is identity, this is identity. But if you go to the right, you go to tau again, right? Because if you read 1, you go back to the same state tau. And then you just have exactly the same portrait as the one from that you've seen above. So you have non-trivial permutation at the first level, and then you act as identity here and as tau here. So you have permutation here and identity, 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 and then tau again, and there will be another permutation and so on. So that will be the portrait of this automorphism tau. It will have these switches only along this rightmost path. In terms of writh recursion, so we record the same data. Well, let's start with identity. You have identity is equal to, on the left tree, it acts as identity. On the right tree, it acts as identity. And then it doesn't permute the vertices of the first level, so that's why it's a trivial permutation here. So I'll just put trivial permutation, but usually people skip that. Once there is a trivial permutation, people just don't write any permutation. Now, tau, on the other hand, if you read 0, you go to identity. So on the left subtree, you act as identity, right? On the right subtree, you act as tau. And then you permute 0 and 1, right? 0 goes to 1, 1 goes to 0. So you have here 0, 1. Okay, so this is a writh recursion defining add-in machine, right? And now we could actually see that it will have infinite order. Remember that we proved that it has infinite order by constructing infinite orbit. So here it's actually a bit easier. So what is tau squared? Yeah, so maybe let's just say for simplicity, let's denote identity by 1, right? So it will create a little bit of confusion, but usually it will be clear because we already have 1 here. That's an element of the alphabet. But on the other hand, this is identity in the group, so we're going to just denote it by 1. So we have tau is equal to 1 tau, and then let's say sigma, and non-trivial permutation 0, 1 by sigma. Okay. So then what is tau squared? Tau squared will be, so let's just try to apply this formula on top. That's going to be 1 tau sigma times 1 tau sigma, right? So let's see, what do we multiply by what? So this one, right, is multiplied by this tau here because there is this sigma that permutes the subtrees. So first you act by the left component, but then you permute the subtrees. You move this left subtree to the right subtree. That's why for the second automorphism, you act by the right component. And the second component is multiplied by the first component, right? Because the second component, the second subtree, is moved by sigma to the left subtree. And so by the second automorphism, you act by the first component, right? So that's why here you're going to have 1 times tau, tau times 1, and then sigma times sigma just cancels out. So we have just tau, tau. Okay, so in other words, if we want to draw the portrait of this tau squared, so tau squared will look like that. It will look like tau on the left and tau on the right, and it will not permit vertices of the first level. And then we know how this tau look like, right? So it will just have these switches along the rightmost paths. Okay, so that will be a portrait corresponding to tau squared. But now we could ask ourselves, so what could be the order of tau? So claim the order of tau is infinite. Why so? Well, so first of all, tau is non-trivial, so it's non-identity element because it permutes vertices of the first level, right? Because of this sigma. And any odd power of tau will permute vertices of the first level non-trivially. So that's why the order, if it's finite, is going to be even. So if tau has finite order, it must be even. Okay, as tau permutes, well, let's say flips the vertices of the first level. Okay, so now suppose that the order of tau is 2m. Well, but then we have that tau to 2m. If tau squared is equal to tau tau, so once you multiply tau tau by itself m times, 2m times, right? No, m times. You're going to have the tau 2m will be tau m, right? And so if this is identity, right, if this is equal to identity, that means that this must be equal to identity and this must be equal to identity, right? Because this is an automorphism of the tree. If it's a trivial automorphism, that means that it must act trivially on the left subtree and it must act trivially on the right subtree. But that will mean that tau to the m is equal to identity, and that's a contradiction. So tau to the m is equal to identity, contradicting to the fact that order of tau is equal to 2m. Okay, so thus order of tau is equal to infinity. Okay. So this is the first example where you could use with recursion to defer something about the order of an element, right? That's kind of general procedure to find the order, which doesn't always work, but it works in many cases, especially if you have some identities. So we are kind of for the first time see the importance of contraction, right? So contraction means that if you start from a word and consider its sections on the first level or maybe somewhere deeper, the length of these sections go down, right? So here we had length 2, here we have length 1. And so that could be generalized to the notion of a contracting group, which has connection to holomorphic dynamics, to fractals. This theory is mostly developed by Nekrashevich. There is a beautiful book called Self-Similar Groups, which describes this connection deeply. And so it's a very beautiful connection. Unfortunately, we do not have time to go over that in these 3 lectures, but this is where I would suggest you to read about that. All right, so we can sometimes talk about the word problem as well. So this is the order problem. Now, word problem. So suppose you have an automaton group, right? And you have, so what is the word problem? Of course, that's one of the 3 algorithmic problems in group theory, right? So given G, which is a finitely presented group, S is finite, right? And given G is equal to S1 to plus minus 1, S2 to plus minus I. Well, let's just do that. Sk to plus minus 1 with Si in S. Determine whether G is equal to 1 in G. Okay. So you write a word as a product of your generators, and you ask yourself whether this word represents a trivial element in the group or not. So for many groups, we can solve the word problem, and groups generated by automata is one of those as well. And again, we use the with recursion for that. So we can solve it in self-similar groups. So how to do that? Well, if you have a word, well, to be more precise, not just self-similar, but finitely generated. To be more precise, yeah, sorry. So because actually you cannot solve the word problem in finitely generated self-similar groups, you have to restrict yourself to finite automata. So my apologies. I'm just a little bit in a rush now because I wanted to cover a little bit more, but that's okay. So let me just be a little bit more precise. We can solve it in groups generated by finite automata. And
Can
so,
I ask
yeah,
a question about finitely generated group and word problem? As I remember, such a theorem of Buna-Higmana, which said that if a group is finitely generated and it's embedded in the prime in simple group, which is finitely presented, then word problem is solvable. Is it Buna-Higmana really theorem or not Buna-Higmana?
Well, that's Boone-Higman conjecture actually, and so there were quite recent results in this direction, beautiful results by Bleek, Matucci, and Belk and Zaremsky, who kind of proved that this Boone-Higman conjecture works for hyperbolic groups, and the proof actually goes through the groups acting on trees. So. There were earlier results by Nekrashevich in this direction as well. So yeah, so for these groups, it works, right? But in general, that's not a theorem, that's a conjecture, Boone-Higman conjecture.
Aha, the group on the trees is hyperbolic groups.
No. So they are not hyperbolic, but the point of that argument is that for every hyperbolic group, you construct certain tree such that your hyperbolic group acts on the boundary of this tree, and then you use the generalization of a contracting group essentially to show and to use the tools from this theory of group generated by automata to show that you can embed those groups into finite into simple groups, not finite, of course, into simple groups. Yeah.
Thank you. And who solves it? The names who solve it to read it, this
It's
conjecture.
Bleek, Belk,
Bleek.
I think Matucci, and Zaremsky. I think that these are the four.
Thank you.
Okay.
Another question. When you say
so I have just a couple of minutes, so maybe let me just.
Sorry, could I ask also a question?
Yeah, sure.
When you say solve it in group generated by finite automata, you mean that by solve it you mean that we can construct an algorithm which solves it for any group from this class when we give a presentation?
Yeah, exactly.
A word. Okay.
And moreover, you can make it uniform, so you could take a group as an input as well, and still there is an algorithm. So it's the same algorithm for all groups generated by finite automata, essentially. Okay, so let me just give a quick example. So let's do Grigorchi group. Right, so let's say, for example, so of course I have given you an automaton before, and now I can just write this automaton in the form of with recursion. B is equal to AC, C is equal to AD, and D is equal to 1B. Okay, so that's a with recursion corresponding to Grigorchik automaton that I gave at the end of the class. Right? So let's see, for example, that B squared is equal to 1. Right, so what is B squared? So B squared is AC times AC. So there is no permutations here. That's why we just multiply like in a direct product. So that's going to be a squared, c squared, right? And we kind of start building the portrait. So b squared is a squared and c squared, right? So let's see what is a squared. A squared is 1 sigma times 1 sigma. Right? And so we multiply this one by this one, and this one by this one, because of this sigma here. But 1 times 1 is 1 anyway, and sigma cancels this sigma, so we have just 1. So that's why this is identity here. Identity, and there is no need to develop this further. Let's look at c squared. So c squared is, c is AD, so you have AD times AD, and you have then a squared, d squared, right? So a squared and d squared. We know already that a squared is 1, right? Because a squared is 1, so that's why it's the identity. So the only thing that we don't know is d squared. D squared is equal to 1b times 1b, and that's going to be 1b squared, right? So we extend our portrait here. You have 1, and you have b squared, but now you say, oh, well, so we have seen b squared before. So whatever happens below here is the same as happens over here, right? If we haven't seen any non-trivial action from here to here, there will be no non-trivial action below, right? So that's why this is equal to identity. So you have that b squared is equal to c squared is equal to d squared is equal to a squared is equal to identity. And that's just a specific example how to solve it, but you could see that it works in general. Why? Because once you take, if you have a finite automaton where the sections are again the states, right? So here you have a section which is again a word of length 1. If you take a word of length 2, its sections will be again words of length 2. If you take a word of length n, its sections will be words of length n. And once you go deeper and deeper and deeper, you will circle through a finite set of sections of words of length n. And sooner or later, you're going to see the repetition. Once you see the repetition, you can stop. There's no need to go down because you have seen what will happen already, right? So that gives you the solution to the word problem, essentially. It's going to be generally exponential solution for the class of some certain subclasses of groups like contracting groups. You can actually have more efficient algorithm, polynomial time algorithm, but definitely can solve the word problem here, right? And probably I will be forced to stop here. So check that BCD is equal to 1, right? And that will show that B, C, and D, this group generated by B, C, and D, is just isomorphic to Klein group K4. Okay. So I'll stop here. And again, I didn't cover everything that I wanted to cover, but we are getting close to Grigorchi group, and probably next time we'll be able to show that Grigorchi group is infinite periodic group.